quantum mechanics was and is the hardest class I've had in my undergraduate studies so far. It's very unintuitive, and I have had a lot of difficulty understanding why I should care about it. And I'm making this video because I think I've finally found my own reasons why it's important and why I think other people might also find it important. It did take me over a year of just thinking and being in the back of my head, just why should I care about this stuff? But I think I got very lucky this semester at UC Berkeley to have a physics professor who was good enough to break it down to the point that I see why it's as important as it is and why I should care about it. I'm a chemical engineer. We deal mostly on the macro level of things, so why you need to care so much about explaining the atomic level interactions can sometimes seem trivial and unnecessary, but it is a very important discipline in science, and hopefully this video will be able to encourage or help out some other people who had the same struggles that I had going through school, wondering why the heck should I be doing quantum mechanics. So to start off with, the purpose of any science discipline, be it biology, chemistry, or physics, is to explain, control, and predict the world around us. And so this very important term, explain, is something that in the early 1900s, physicists thought they had. They had Newton to model classical mechanics and all these particle interactions and what happens when you have objects moving down an inclined plane at a certain angle theta with particular resistances and all these values. You've got electricity and magnetism, and once the last hurdle that scientists thought they had to cross was Maxwell's equations, which defined the behavior of electricity and magnetism and photons. So once people got that far, they were pretty sure that there was nothing else to really care about in physics, and it was a closed case. And for me, the really cool thing that I realized recently was it parallels so closely your studies as an undergraduate student in college. You've taken all these classical mechanics courses and you've followed the history of Newton and Maxwell and all these other key figures who were able to, you feel like you can explain everything in the world that you see pretty easily. And that's what physicists felt too at the time, until you get down to the level of atoms. And so my point is, though, that there's just this beautiful historical parallel that it's very cool. It's like in my mind, it's like you're a physicist during the 1900s as you're taking quantum mechanics, going through all the challenges and all the questions and all the perplexities, if that's a word, that people are going through. And so it's very cool. And I just want to say the whole purpose of this video is to try to get you to understand why quantum mechanics is important, not necessarily define ad nauseum all the theories and principles and everything else. I might get a tiny bit into that stuff unintentionally, and I cannot speak to the accuracy of any of it. So take everything with a grain of salt, but I just want people to be able to see why it's as important as many physicists claim it is. And so, with that being said, why did classical mechanics break down in the first place? And so if we think of the traditional view of a proton, so hydrogen atom running around with a nucleus. We've got this proton here, an electron spinning around the nucleus. And our intuition tells us that this electron is just a simple particle, and you can easily define completely its position and momentum, its energy, and its time interval, exactly where it is. And consequently, we can apply all of the traditional equations we've been used to in classical mechanics, such as Coulomb's law of interactions and all these orbits and all these other formulas involving periods and frequencies. And what we find is that for an atom to have the same properties, for a hydrogen atom to have the same properties everywhere in the universe, this radius needs to be identical in everything. And at first that was a very hard thing. That was a hard pill to swallow for many physicists, because if you treat this electron like a particle, depending on its environment, you should expect different properties. Perhaps the electron is going to start spinning a little bit more fast, more quickly, and it's going to get a bigger radius, or it's going to spin more slower, and you get more slowly, and you get a smaller radius. But what they found was no matter what hydrogen atom they looked at, anywhere in the universe, they got the same exact properties. And that was confusing to a lot of people. So this notion that this electron is just this particle that we can assume is a particle, an object that we can assume is a particle, was not looking too great. And the other thing was, assuming that there is this electrostatic interaction between the positive proton, or protons in the nucleus, if it's got a greater atomic number than hydrogen, and this negative electron out here, you would expect the electron to eventually fall into the nucleus, and we would be seeing, as its angular momentum decreased as that happened, a consistent emission of energy from hydrogen atoms, which we just weren't seeing. And the main point is that at the atomic level, classical mechanics fails. So everything you've learned in chemistry and physics beforehand that told you to think of hydrogen and all these other atoms as just these little nice little things with spheres and everybody was happy, it no longer works as well as it does. And the other reason why classical mechanics fails us is if we take water for example, we've got oxygen and two hydrogens, and we've got covalent bonds between these oxygen hydrogen atoms, and that means that they are sharing an electron. What that means is, depending on where that electron is around this water molecule, you will see a different property of water. So if you had a solution of water, you would expect to find that each water molecule behaves a tiny bit differently than the others, because of the fact that you're treating your electron as a particle. And so that notion that we can do that was proved wrong experimentally, because every single water molecule you look at is a water molecule. You don't have water molecules with the electron here behaving a little bit differently from water molecules with the electron here. And so, again, the particle notion applied to an electron was failing physicists, and it was irking a lot of people like Einstein during the 1900s with this idea. And so now you may ask, why did we even think that electrons were particles in the first place? And so there was this guy named J.J. Thomson in the late 1800s who devised an experiment where he had an ion source and a detector, and what we would get when this ion source emitted some new particle that hadn't been discovered yet was a definitive click. Okay, so when you hear a click, you think of a particle hitting a piece of paper or a detector or something. In addition, when you double the intensity of your source, you double the number of clicks, which again makes us think that whatever this new particle that hadn't been discovered yet must behave like a particle. And so that was the idea that physicists had for a long time until Young came along and devised the double slit experiment, which you've probably heard about in electricity and magnetism or waves and optics, where you've got two slits here, and as photons, this is the key distinction between Young's experiment and the other one that was done later. But when photons were emitted from this source, we get this diffraction pattern. We've got a local maximum and dark spots, just like sound waves. So that idea that photons also behave like waves was an interesting concept to people, but it wasn't until people instead did this with electrons later on. I believe it was two German scientists, and they just modified some things, but it was essentially the same thing, except you have electrons flowing through it's a different kind of media. But what they found was the same exact thing that Young found when he emitted photons from the source, which was you get this weird double slit pattern. Even when you send one electron through, you get a double slit pattern, which doesn't make much sense to anybody if it's a particle, because by definition, if it was a particle, you'd see, depending on where it, all the possibilities, you get these, scatters here, but they weren't getting that. They were getting so I don't want to beat the bush on this one. And so another thing that distinguished this electron diffraction pattern on this plane from what was to be expected from a particle was this idea that if you covered up one of these slits and observed the diffraction pattern that you got when an electron passed through, and then if you covered up the other slit and let electrons pass through that one, if you added those two diffraction patterns together, if electrons were particles, you would expect it to be the sum of the two individual slits. However, that's not what was observed. What was observed was a diffraction pattern. And so we keep alluding to this theme that even though electrons behaved like particles when they were first discovered, they do have wave-like properties. And so what I was trying to get at before with this Young's slit experiment was, as your electrons, when you have both slits open and you only have a single electron passing through, you get a double slit diffraction wave-like pattern. So it's like the electron is passing through both slits simultaneously, even though supposedly you only have one particle, which doesn't make any sense. And this baffled the scientists who were performing this experiment with electrons. And so what they did was they put a little detector at each slit. And during their double slit experiment, you had both slits open. When electrons flowed through the two slits, what they found was, as when they had the detectors here, the electron behaved exactly like a particle. But when you take the detectors away, what you find is that it behaves, the electron diffraction pattern you get without the detectors is like a wave. So as soon as you observe or place a detector at the slit, and the electron can still pass right through, it acts like a particle. And so there's this definition people have to battle with in physics. What is observation? What does it mean to observe something? And the problem with quantum mechanics is that observation is an act itself. You are interacting with the system you're studying by observing an electron, as it passes through these double slits, caused it to act like a particle. But when you take these detectors away, it acts like a wave. And it was a pretty funny analogy in our physics class. Our physics teacher was telling us it's exactly like people. When you know you're being watched, you behave differently than when you do when you're alone. Electrons are exactly the same. And it's very, so we see this stuff experimentally, and how you are able to define and describe it becomes such a huge challenge for people. And in terms of an introductory physics course, quantum mechanics course, you'd hold off defining what it means to observe something until much later on. So Feynman said, essentially, just ignore what it means to observe something. Just look at the experimental data results and go with it. And I'll briefly touch on why we see electrons behave this very strange way relative to what you would expect. So why does an electron behave like a particle and a wave? So the answer to that question is, in everything in this world, you and me, everything in this universe has both wave-like and property-like properties, or particle-like properties. Consequently, I have a wavelength, you have a wavelength, everything has a wavelength, even though on the macro level we look exactly like particles. The question is, why is that? It's because the more massive an object is, the less wave-like its properties become. Or I'm sorry, the more massive something is, the lower its wavelength, smaller its wavelength. So with something like my hand or this pen, it is so massive that relative to an electron or a photon, that while it has wave-like properties, its wavelength is so incredibly small that we can neglect it and treat it as purely a particle. Whereas with something as tiny as an electron or a photon, because the mass is so small, the wave-like properties of it are not negligible anymore. And that's why we see electrons behaving as both particles and waves. And an interesting thing to touch on while I'm at it, something I thought was pretty cool just from the early stuff I've read, was this notion that, and if you follow physics a little bit, you've heard of Heisenberg's uncertainty principle. If you watch Breaking Bad, you've heard Heisenberg. One of his contributions to science was this idea that the more precisely you define an object's position, the less precisely you can define its momentum. That's the Heisenberg uncertainty principle. So what it means is that you can never simultaneously know both an object's position and momentum at the quantum level. And this is what I think chops a lot of people off at the knees, myself included, when we were trying to learn quantum mechanics, was this idea that in the real world, when you use Newton's equations, you can say, if I drop this pen, it'll take 200 milliseconds to hit the ground based on all these equations, and you can define precisely an object's position over time, and you can calculate its momentum all the while and do all this stuff and know everything there is to know about this object as it falls through space. You cannot do that in quantum mechanics. In quantum mechanics, you can only you can only have one, or you can have a mixture of the two, but to an extent, and it's defined. I won't write down the math equation just to keep things simple. The main point is just get the concept. The other important concept is this idea that the more precisely you define the time interval, this delta t value, as you let this approach zero, get infinitesimally small, the energy value of anything goes up. And it goes up so high that, according to Einstein's equation, E equals mc squared, if you have a high enough energy value, something will take on a mass. And so what you get is the creation plus annihilation, if I can spell it, of virtual particles. Virtual particles are things that quantum physicists use to describe things that actually do exist in real space, but you just can't see them because they exist for such a small amount of time. And you may say that's great and who cares? Unless you can prove this experimentally, what good is it? And so fortunately there's something called the Casimir effect, in which we have two metallic plates that are separated only by a few nanometers. And the key traits of these are they're both neutral, they're both in a vacuum, and they're metal, and they're separated by a very small distance. And so this idea that as our time interval approaches zero, we can have the emergence and annihilation of virtual particles applies to this situation. It's been proven experimentally. If these two plates are only separated by a small enough distance, there will be, in free space, because there's nothing else in this system other than space and these two plates, the creation and annihilation of virtual particles. And so what ends up happening is, because you've got a lot more space on the outsides of the two plates than you do on the inside, you have more virtual particles here than you have on the insides of the two plates. And the result of this is you are more likely to have these virtual particles hit and bounce off the sides of these walls than you are to have virtual particles hit and bounce off the sides of the inside walls. And so what you end up getting is these two plates get pushed together, no electric interactions, nothing else other than these virtual particles is causing them to come together. And I think it's really cool stuff. I hated quantum mechanics the first time I learned it, because after the first few lectures at Berkeley, it just turned into a huge mess of not being able to follow anything anyone was saying. And people might as well have been speaking another language, because none of it was clicking, and I couldn't see why it mattered. And so I dropped the course after the first week, but I have to take it for my major. So I've spent the last year just kept asking myself in the back of my head, why should I care about this stuff? Why is it important? And eventually I've been lucky enough to have a really good teacher who was able to explain it to me. I hope if any of this is able to stick to anybody and make them realize why quantum mechanics is relevant to anything in their life, or not, maybe it'll help them see the beauty of science and like it as much as I do. But thank you guys for watching, and I hope this means something to someone.